Our third talk is rather interesting, and I'll explain why in a second. It's titled The Dissolved Oxygen Sensor Test Set. It's being done, being sponsored by a company called Seabird Electronics in Belgium, and their mentor is Vlad Simonton. Vlad, here, here's your hand. What's interesting about this is Vlad is one of our graduates. A few years ago, Vlad was up here, not in this room, talking about this capital project. So now we've gone full circle. Vlad is now the mentor to the team. So we really appreciate that. Appreciate Seabird for sponsorship. Again, Eric Sotom is the faculty affiliate mentor. And I'll turn it over to the team.
Thank you, Arnie. I would first like to give special thanks to both Vlad and Seabird. Without their immense cooperation with us, this project probably would have been impossible. I am Colin Stavision, and my members are Michelle and Eric, or sorry, Stephen. And our faculty mentor was Eric, Dr. Eric. So this is Seabird. Seabird is the world's largest developer and manufacturer of products used to measure ocean parameters. So they have these sensors, and they can measure oxygen, pressure, temperature, and whatnot. And they are used by a variety of industry to measure things like climate change or other environmental events. Our project focuses on two of Seabird's dissolved oxygen sensors, the SPE43 and SPE43F. The SPE43 outputs a DC signal between 0 and 5 volts, and the SPE43F outputs a varying frequency. And this depends on the oxygen content of the water. Project overview. So currently, the testing process for each one of these bores involves a technician manually using an oscilloscope and digital multimeter to check test points. This technician then manually fills out documentation, and based on the documentation, he is able to determine if the bore is within tolerance. We were going to automate this process. Ideally, the SPE43 and 43F would be secured to the test fixture, and then a program would be initiated by a PC. The fixture then runs through a program and connects to each one of the test points to find measurements. The fixture then sends these results back to the PC. Design concept. So the main driving factor in our design was the fact that both the 43 and 43F have portions of their circuit board which are both isolated and non-isolated from ground. And our circuitry needed to mirror that. So we have a split plane. One references ground while the other references the device under test. Our design was split up into 4 parts: signal conditioning, capacitor resistor selector, power supplies, and microcontroller. Signal conditioning is responsible for signal retrieval and signal conversion. The capacitor resistor selector is responsible for connecting certain components to each one of the devices under test, because during the test procedure it needs to have different capacitors or resistors connected to each one of the circuit boards. The power supply is sort of self-explanatory, it powers the circuit and the sensors, and the microcontroller controls when and what signals are to be measured and also communicates with the PC. The first portion that I was responsible for was the signal conditioning. So why do we need signal conditioning? Our microcontroller has a limited range of signals that it can actually read. For voltages, this is between 0.5 and 4.7 volts. So this is an example of the isolated side of our signal conditioning circuit. In the upper left-hand corner, we have our test probes. These retrieve the signal and then are put through a quad op amp, which acts as a buffer. These signals are then sent to a multiplexer, which the PSOC controls which signal it actually wants to measure. The signal is then converted to a frequency and then sent through a digital isolator, which will convert the signal from one ground plane to another ground plane, which the PSOC is on. It can now read the voltage that it measured as a frequency. Some additional hardware that we use in other parts of the signal conditioning schematic were instrumentation amplifiers, digital signal buffers, and voltage dividers. I was also responsible for the PCB design. The board is comprised of 4 layers. The top and bottom layers house the signal traces. The second layer houses the split ground plane of isolated and non-isolated, and the third layer is all power traces. One of the main critical aspects of this board was the location of each one of the test pins. To get around this, we had a AutoCAD file given to us by Seabird, which has locations of each one of the test points for the sensors. We can then import this file into our PCB schematic program and then design directly to each one of the boards, placing each one of the pins. The last thing that I was responsible for was the enclosure design. I modeled the entire thing up in AutoCAD, and then I was able to customize around the PCB. I then created 2D drawings of what needed to be customized and made, and then sent them to Seabird for a milling. And then Steve is going to take you through this portion.
Thank you, Colin. The power circuit for the test set features an input voltage of 24 volts. It has an isolated ground plane and a non-isolated ground plane. With the non-isolated ground plane, we have a plus minus 12 volt power supply along with a 10 volt power supply, a 5 volt power supply, with a 3.3 volt power supply piggybacked onto the 5 volt power supply. The reason why we do this is to reduce the power dissipation that would be needed to convert the 24 volts down to 3.3 volts, and it also allows us to use a smaller chip size for our power supply. Now on the isolated side, we have a plus minus 12 volt isolated power supply that is piggybacked by a 3.3 plus minus isolated power supply, and the reason why we did that was for the exact same reason as for our non-isolated power supply. And lastly, we have the plus 6.6 isolated voltage in the isolated ground plane. And one of the cool features about our power circuit is our current sense. So as you can see, you have 3.3 volts coming for our power supply going to the device under test. And how the PSOC monitors how much current is going through, you have the current sense chip right here. It reads the voltage off this 1 ohm resistor and reports it back to the PSOC through the multiplexer, where the PSOC can actually make the decision whether or not the current is over or below the specified range. Now the selector circuit you see on the top is a resistor selector. What this does is it chooses the proper resistor based on the model number of the device under test. And also we have the capacitor selector on the bottom, which has a default capacitance of 180 picofarads when it first begins, and then after it runs a test around the middle of the test procedure, it tests the gain or the frequency depending on which model we're testing, and chooses the appropriate capacitance for that value. Now if the capacitance does change and the selector chooses a different capacitor, the portion of the test that was just ran is reran to make sure that all of the values obtained are still valid. So one of the difficult parts of this circuit is actually the relays that were used. We initially started off with the electromagnetic relay, which had about 80 picofarads across the switch, which proved to be by far too much capacitance for our lowest capacitance selection, which is only 47 picofarads. So after some research and digging, we found solid-state relays that use photo-MOS technology that considerably brings down the capacitance value to about 38 picofarads, which is within a reasonable tolerance. So now the proof of concept for our PCB board, when we first received the PCB board, the first thing that we had to do was check the isolation between the ground and isolated planes. Once that was complete, we had to verify that the PCB board could actually handle the 24 volt input voltage. So the way we accomplished that was we hooked it up to a power supply and slowly turned up the voltage until we hit our 24 mark to make sure that no components were damaged or the board wasn't damaged from unseen connections or defaults, or excuse me, defects, miswired components, or possibly a short to ground. Now once that was complete, we started testing the power supply section. This proved to be very difficult because of the isolated ground planes and the multiple power supplies used in the power section. And not only that, a lot of components use both, well, they use both isolated and non-isolated ground and multiple voltage supplies, so this proved to be extremely difficult to find problems. And lastly, we did voltage generation verification for our AC signal. In addition, we performed amplifier gain verification. How we did this, we inserted a known voltage from our test device into the pogo pin and looked at the output of our operational amplifiers, our instrumentation amplifiers, and our isolated amplifiers to make sure that the proper output voltage was received at the PSOC microcontroller. And as you see, we went through all these verification tests, and the last test we did was the linearity relationship between the voltage to frequency conversion for the voltage to frequency converter. As you can see on the left-hand side, we have the expected frequency versus voltage, which is a nice perfect linear line. And then on the right here, we have our measured frequency and voltage, which is also a very, well, pretty close to a linear line, and we were very satisfied with those results. So the modifications that we had to perform to the PCB to actually get it to work was when we first received our PCB board from the stuffing company, well, actually the company that put the components on the PCB board for us. We found that we neglected to tell them which side we wanted the components on the PCB board. So once we received it, we had to reorientate the components to the proper side and verify through through resistance testing or continuity test. And another problem that we had to fix was one of our power supplies had a footprint that was way too small for the size chip that we had, so we had to jumper in a adapter with the chip on it so we could provide the circuit with the needed voltage for that part. And lastly, one of the improvements that we had to make was to remove the low-pass filter that was on our plus minus 12 isolated and non-isolated power supplies. What was happening was the low-pass filter was actually distorting and adding loss to our power supplies, which is not ideal, so we actually removed those and fixed the problem that way. And now here's Michelle to talk about the PSOC.
For this project, we used the PSOC-3, which is an industry spec programmable system on chip. It's unconventional to a traditional microcontroller and is made up of several subsystems. As a digital system, it has an analog system and a CPU like a normal microcontroller would have. However, because of the way it's designed, it's more flexible and allows for more optimal programmability in industry. So this is our hardware schematic design, which was done in PCB Artist, as was all of our schematics throughout the course of the project. For this project, we're using UART communication, so we have a MAX 232 line driver at the top here, which is connected to a Molex connector, which would then be on the outside of the box, and to connect to the RS-232 connection, which goes to the PC, and the user interface for communication. The PSOC itself is going to be programmed with the MiniProg-3, which would connect to this Molex connector here. Also, we chose to utilize both the 1 megahertz crystal as well as the 24 kilohertz crystal for flexibility throughout our design. However, the 1 megahertz crystal allows for most optimal clocking for the PSOC. We have several digital outputs, which control our voltage mux, our frequency mux, our capacitor selection or resistor selection, our test LED, our power LED, or not power, but testing LED, and then when test is in progress LED, and to initialize our 3.3 isolated voltage. We also have an analog to digital input, which takes a voltage from the voltage mux to the PSOC and 3 frequency inputs, which would go to the frequency counter inside the PSOC. For our firmware specifications, our initial intention was to design firmware which performed a series of automated tests and return results, and we did use C for this. Our digital hardware selection control is actually complete, so we made all of our selection functions that control all of our external hardware. Also, our PSOC actually does read voltages and has been tested. However, for future reference, we would suggest that a calibration routine was done to improve the design. We unfortunately did not get to our frequency counter, and we also have functions for our UART communications. Because PSOC is industry standard, there are less open source resources for programming, and proved to be quite a bit of a challenge. The user interface itself will be designed by Seabird, and we've set a solid foundation for them to do that. We confronted several challenges throughout the course of this project. Of those, time and scope are definitely the two that have proved the most challenging. We have had problems with dividing workloads for maximum productivity, and also manning issues that we encountered throughout the project. And documentation, which I'll talk about in a second. Our isolated circuit itself was something that we figured out later on in the project. We had already started our design for the project in the first quarter, unlike a lot of the other teams. And at the latter portion of the first quarter of capstone, we discovered that we needed to change this isolated circuit and collaborate to do to alter our power circuit. What we learned is don't take on too much if possible. If you can foresee the scope of the project and make it into something that is tangible and that will be able to be tangible and possibly more reasonable, you should think about what your other options are earlier on. Document your hardware so that software specifications are clear and concise. So our group, we actually divided out, because the hardware was so immense, we divided out portions of our hardware. In order to make software specifications, we had to follow back our hardware and try and make good specs for the software. Since we have several inputs and outputs, this proved to be a challenge, just because of the amount of the scope that we were looking at. Also, communication is something that is key in any team project. Had we communicated clearer earlier on, we possibly would have found some of our issues earlier on and been able to work together to get through it. In conclusion, we have tested our hardware, and for the most part, our hardware, other than integrating the test box itself, works to specification. Our firmware, we've set up several functions which Seabird can use to generate the automated tests for the test box, which there, I believe, is over 50 tests that would need to be automated. And our final outcome is a very solid foundation for Seabird. Any questions?
For all the power supplies, is it designed to just receive a plug from the wall? I mean, obviously
Yes,
it's
sir.
controlled.
Yeah, so we had a 24-volt wall board that converted AC to the 24 volts that we needed.
Okay.
For those of you who took 425 with me or will take 425 microprocessor design class, remember, I taught voltage to frequency conversion, split planes, and optical isolation.
Right.
Another question? One question.
How much experience did you have with PCB design before starting this project?
I had designed one PCB prior in his class, and I attempted to do our projects, and it turned out pretty good so far.
I also had one PCB design. But Colin did all of the organization and the actual putting it all together.